Alright guys, so what we look at next is the NOR gate implementation of the active high SR latch. So what you see on screen here is the logic circuit of that SR NOR gate implementation. And what I want you guys to notice is, first of all, the NAND gates from the NAND gate implementation is replaced by NOR gates, of course. And another thing is, set and reset have swapped positions, right? Set used to be in the first input, now it's in the second. Reset used to be in the second input, now it's in the first. Now you can either make this swap as the inputs change positions, or you can change Q to be in the position of Q complement and Q complement to be the position of Q. You have to make either the output swap or input swap in order for this to make sense. Other than that, everything else should stay the same. Let's look at how a NOR gate works. First of all, a NOR gate is effectively an OR gate, but the output is negated. So therefore, 0 NOR 0 would be 1, 0 NOR 1, 1 NOR 0, and 1 NOR 1 will all be zeros. Now again, just like the NAND gate, we need to assume that this gate starts off with some configuration without which we can't realize the starting position of the gate or the circuit. So let's imagine that the gate starts off in this sequence where set is 0, reset is 0, Q is 0, and Q complement is 1. Let me write those sequence of outputs here. Q is 0 and Q complement is 1. Let's say that we make one change. Let's say that we change the set to a 1. What changes will the circuit go through? So this 1 is received by the NOR gate, and so is the Q's 0. 0 NOR 1 based on the truth table is 0. So the Q complement changes to 0. This 0 passes through this circuit and becomes a 0 as the input for the above NAND gate. 0 NOR 0 would be 1. So this would change to 1. This 1 gets passed down. This 0 changes to a 1. 1 NOR 1 settles down at 0. Now it's stable. So what happened is Q changed from 0 to 1, and Q complement changed from 1 to 0. So you can probably realize what's going on here. Unlike earlier where we needed to change the set from a 1 to a 0 in order to change the Q to a 0 to a 1, now we change the set from 0 to 1, meaning we activate or make the set input high to change the input from 0 to 1. So it's the same input change, but actually it's the same output change, sorry, but the inputs are different. Earlier we changed a 1 to a 0, now it's a 0 to a 1. And since we make the input high or 1 to result in a change in the output, we call this an active high circuit. So the NOR gate implementation of the SR latches or SR flip-flop is active high. Let's look at the rest. So starting off from this configuration where we left off, let's do the next. So we are now trying to set the set bit back to 0. Let's see what happens. If you set the set bit back to 0, this will change to 0. 0 NOR 1 is still 0. So we are still in the stable state, which means that it will remember whatever was previously put in it. So you can probably realize that earlier it was 1 1 that was the memory state. Now it's 0 0 that is the memory state. Let's make another change. Let's make the reset to 1. You might already be able to guess that it should probably make Q go back down to 0, right? Let's see if that's the case. Let's change reset to 1, keeping the set as the same thing. This will change to 1. 1 NOR 0 would make Q a 0. 0 goes down here. 0 NOR 0 would become 1. 1 propagates up here. 1 NOR 1 would be 0. So it's now settled down in the stable state. So resetting or setting the reset input to 1 would cause Q to go back to 0 and Q complement to follow and become 1. So now you're back in the original state where Q is 0 and Q complement is 1. Right, so we've gone through the same series of outputs with several different changes of inputs instead. And finally, you might be able to guess what happens if S and R are both 1. Let's say I change S back to 1. What are the changes that it will go through? 0 becomes a 1, 0, no 1 would be 0, 0 propagates through up here, 0, no 1 would be 1 again. So now you have this case where both q and q complement is, actually I made a small mistake, 0, no 1 is 0. Yeah. So now we are in this state where both q and q complement is 0. That is also invalid. So both q and q complement is 0, which results in another invalid state. So this is the NOR gate implementation's invalid state. So what are the states we see here? We see a memory state where both S and R are 1. We see a set state where S becomes 1. We see another memory state. Then we see a reset state where S is 0 but R is 1. And then we see an invalid state where both S and R is 1. So the outputs are pretty similar, except of course the invalid state is now both zeros instead of both ones earlier. But everything else seems to be the same. So if you simplify this truth table, you'll get something like this, where S and R is both 0, memory state is achieved where it remembers whatever was previously put in it. If set is 1 and reset is 0, meaning you activate set, it sets the Q to 1. If you activate R, which means you set R to 1, it resets the Q back to 0. And if you set both to 1, it sort of reaches the invalid state where Q and Q complement are the same, being 0. That's the truth table for SR latch, and that's really how it works. And make sure that you understand that you need to give the configuration a starting value. Either you can give 0, 0, 0, 1, Q and Q complement is 0 and 1, or you can give S0, R0, Q1 and Q complement 0. Similar to the earlier one, you can either start off with one of these two states, one of these two configurations. You should still get a similar set of outputs. But remember, your truth table should be changed accordingly. Right. What are the issues with the SR latch? Two issues. The first is the fault condition. And this is going to be a bit of a problem, although it might seem to us that it's sort of reached the stable state. The issue with the fault condition is that theoretically we are expecting Q and Q complement to be opposites of each other. So if you write programs that work on this behavior and then they assume that this behavior is the case where Q is the opposite of Q complement and vice versa, the programs will crash because Q and Q complement are suddenly the same thing. And when does this happen? In the NAND gate implementation, it happens when S and R are both 0. In the NOR gate implementation, it happens when S and R are both 1, which results in either Q and Q complement both being 1 or Q and Q complement both being 0. That's the fault condition, which will result in crashes in memory and memory problems in the computer if implemented straight away. The race condition is another condition which happens when both inputs change at the same time. So remember what I told you at the beginning of the NAND gate implementation video. I told you that when you make changes from one state to the next, you must make 1-bit changes, not 2-bit changes. As long as you do 1-bit changes, there's no issue. But imagine you make a jump like this, where 1 becomes 0 and simultaneously 0 becomes 1. What happens is, there'll be competing signals going through the circuit, and the resulting state would be non-deterministic, meaning we won't be able to understand what the final state would be definitively. It could be anything. So it's sort of like the starting state of the SR latch. We don't know what the starting state will be. It will just stabilize on whatever state available. So therefore, it's not really deterministic. It's not very helpful for us as programmers to work with the race condition. So therefore, that's another issue that we have with the SR latch, where both inputs change at the same time, resulting in both inputs competing for the output, which might result in undesirable behavior. But that's it, guys. That's all we need to understand about the NOR gate implementation or the active high implementation of the SR latch.